Forecasting and Pro Forma Financial Statements, Forecasting and Time Series Modeling, Learning Module 5, Lecture LM5c. Time series models use historical records from the business or industry to predict future sales. Again, they are often referred to as internal or intrinsic models. There are four types of time series models that I will describe: the moving average model, the weighted moving average model, the exponential smoothing model, and the linear regression model. The moving average model is the simplest time series model. This model assumes that actual sales for previous time periods are the best predictors of future sales. To compute the moving average sales, take the arithmetic average of actual sales for the last several periods, for example 3 months, and apply that average to the next month. The formula is below. Sales sub m plus 1 equals sales sub m minus 2 plus sales sub m minus 1 plus sales m, all divided by 3, where m plus 1 equals next month, m minus 2 is 2 months ago, m minus 1 is 1 month ago, and m is this past month. For example, consider an Old West lifestyle museum in Phoenix, Arizona, USA. The museum forecasts the next month's visits using the moving average model. Visits in June of 2014 were 1,245. In July, they were 1,038, and in August, they were 1,550. The September 2014 forecast was computed as 1,245 plus 1,038 plus 1,550 divided by 3, which equaled 1,277.67 forecasted visits. Actual September 2014 visits turned out to be 1,593. The October 2014 forecast is computed as 1,038 plus 1,550 plus 1,593, all divided by 3, which equaled 1,393.67 visits. The student should carefully review the more detailed section on the moving average model in Chapter 6 of the course textbook, including explanation of terms, the approach of the model, and the figures illustrating its application and computation. The weighted moving average model is also relatively simple. It assumes that previous period actual sales are not equal in their impact on future sales. A common example of this is that most recent month may have more impact on next month's sales than months previous to that, though they do have an impact. To compute the weighted moving average sales, a weight is applied to each previous month's sales to reflect the different impacts. The formula looks like this: sales m plus 1 equals W1 sales m minus 2 plus W2 sales minus 1 plus W3 sales m, all divided by 3, where W1, W2, and W3 are the relative weights of each month's sales. For example, consider that same Old West lifestyle museum previously described. The forecast the next month's visits using the weighted moving average model. Visits in June of 2014 again were 1,245, in July they were 1,038, and in August they were 1,550. This time the following weights are applied. June is weighted 0.1, July is weighted 0.3, and August is weighted 0.6, placing greater importance on the most recent months in forecasting next month's visits. The September 2014 forecast was computed as 0.1 times 1245 plus 0.3 times 1038 plus 0.6 times 1550, all divided by 3, equaled 1,365.9 visits. The September forecast under the weighted moving average model is higher than the moving average model because more weight was given the month of August, which had higher visitation than June or July. The student should carefully review the more detailed section on the weighted moving average model in Chapter 6 of the course textbook, including explanation of terms, the approach of the model, and the figures illustrating its application and computation. The exponential smoothing model is similar in intent to the weighted moving average model in that it recognizes that sales in the current period may impact the actual sales of the period forecasted. The model uses a smoothing constant to account for this impact. A smoothing constant is assigned by the forecaster to allow for differences in impact of sales in the current and previous time periods on sales in the next period. This smoothing constant can take on a value of between 0 and 1. The formula for the exponential smoothing model is Fs sub m plus 1 equals alpha times A sub m plus 1 minus alpha times Fs sub m, where Fs sub m plus 1 is a smoothed forecast for next period. Alpha is a smoothing constant, and A sub m are actual sales for the current time period, and Fs sub m is a smooth forecast for the current time period. That is, this formula says that the smooth forecast for the next period is impacted by the actual sales of the current time period plus the smoothed forecast for the current period. The value of alpha indicates which has a stronger impact on next period's forecast, the actual sales of the current time period or the smoothed forecast of the current time period. As the value of alpha increases, the impact of actual sales of the current time period on next period's forecast increases. As alpha decreases, the impact of the smoothed forecast of the current period on the smoothed forecast of the next period increases. The student should carefully review the more detailed section on the exponential smoothing model in Chapter 6 of the course textbook, including explanation of terms, the approach of the model, and the figures illustrating its application and computation. The time series models discussed so far are all useful for short-range forecasts, usually for the next time period. Tourism business managers and owners need to determine which of these three models is most appropriate for making such short-term forecasts for their own business. And once the model is chosen, how should the particular factors in each model be applied? The key is to determine which model is closest to predicting actual sales from period to period. In making such a determination, the following 4 questions should be asked. Which is the most appropriate model for forecasting? The moving average model, the weighted moving average model, or the exponential smoothing model? If the moving average model is most appropriate, how many months should be used to measure the moving average? If the weighted moving average model is most appropriate, what weight should be applied to each month's sales? If the exponential smoothing model is most appropriate, what value for alpha should be used as a smoothing constant? For all models, the computation of the mean absolute deviation, or MAD, is used to answer these questions and determine the best forecasting model. This method serves to measure the absolute differences between sales forecasts for each month and actual monthly sales. Absolute deviations do not consider positive or negative values in the computation of differences. Rather, all the differences are measured as positive. Basically, MAD is the average deviation between a sales forecast for a particular month and the actual sales experienced in that month. Absolute deviation is explained with this example. If you forecasted selling 50 downhill ski lift tickets on Thursday and actually sold 55 lift tickets, this would reflect an actual deviation in sales of lift tickets of +5, representing an increase between forecasted and actual sales. If you forecasted selling 75 lift tickets on the following Friday and instead sold only 70, this would reflect an actual deviation of -5, reflecting a decrease between forecasted and actual sales. The absolute deviation between forecasted and actual sales for both of these days would be +5. The mean absolute deviation for the month of December, for example, would be computed as the arithmetic average of absolute deviations over the course of 31 days in December, noted by the following formula. MAD is the summation of actual sales minus forecasted sales, the absolute deviation of those, all divided by n. This says that the mean absolute deviation is the sum of each of the 31 daily absolute deviations between actual sales and forecasted sales for the month of December divided by n, or 31 days in December. The best forecasting model to use would be the one that resulted in the lowest mean absolute deviation, reflecting the lowest error between forecasted sales and actual sales. This table shows the process of arriving at and evaluating two moving average forecasting approaches using the mean absolute deviation statistic. This table provides the monthly sales for each of the past 2 years with the assumption that we are now in the month of January for year 3, showing the actual monthly sales and forecasts for the previous 24 periods and the next period for a total of 25 periods. This table also shows monthly forecasts using a 3-month and a 4-month moving average. The financial manager of a tourism business can use any number of months he or she deems adequate for the purpose of making strong forecasts. The forecaster would take into account factors such as seasonality, business cycle, and others to determine how many months might be appropriate in developing this table. In column 4 of this table, actual sales for each of the past 24 months are presented. In column 5, forecasts made using the 3-month moving average are shown. Remember, these forecasts are simply the average of actual sales for the immediately preceding 3 months. In column 6, numerical deviations between actual and forecasted sales are presented. If actual sales were greater than forecasted, the deviation is a positive number. If forecasted sales are greater than actual sales, the deviation is negative. At the bottom of this column is a summation of these actual deviations. Over the course of 2 years, there was a mean deviation of only 2.95 unit sales. Notice I did not call it a mean absolute deviation. It is not that. Although this seems small, examination of the column shows some months' deviations were quite positive, for example, December of year 1, and some months whose deviation was quite negative, for example, August of year 1. Therefore, large positive and negative deviations washed or canceled each other out when computing the mean actual numerical deviation. This mean deviation of 2.95 units does not take into account the high variability seen when examining the forecasts and sales month by month. Now look at column 8, which shows the 4-month moving average forecasts, which are simply the average of the immediately preceding 4 months for each time period. Columns 7 and 9 present the absolute deviations between each monthly forecast and actual sales figures for the 3-month average approach and the 4-month moving average approach, respectively. All deviations are positive as defined by the term absolute deviation. That is, positive and negative differences between forecasted and actual sales are treated the same. The effect is that the accuracy of each month is presented. and a difference of 15 units of forecasted versus actual sales reflects the same accuracy regardless of which is higher. At the end of columns 7 and 9 is the mean absolute deviation, or MAD, for each of the two moving average models. This number reflects the average monthly difference or accuracy between forecasted and actual sales and does not have the effect of washing out positive differences in some month with negative differences in other months. Examining the two moving average approaches, the mean absolute deviation for the 3-month approach is 12.16 units per month. The MAD for the 4-month approach is 11.61 units per month. This suggests that the 4-month moving average approach is slightly more accurate on a month-by-month basis than is the 3-month moving average approach. This table shows 3 weighted moving average forecasting approaches using the mean absolute deviation statistic. It shows much of the same information as the previously discussed MAD table for the moving average forecasting model, including 2 years of monthly historical sales data with the same actual sales data as the previous table. After the actual sales data, the table shows 3 approaches to using this model. It shows the use of the model using a weighted scheme for the 3 months previous to the forecast months in columns 5, 7, and 9. W1 is the importance weight for the month 3 months prior to the forecasted month. W2 is the importance weight for the month 2 months prior to the forecasted month. And W3 is the importance weight for the month immediately prior to the forecasted month. For each approach, the importance weight increases as the month considered is closer to the forecasted month. That is, W3 is greater than W2, which is greater than W1. The table also shows the computation of the mean absolute deviation for each of the weighting approaches in columns 6, 8, and 10. The computation of MAD is identical to what was described for the moving average forecasting model. Looking to the bottom of the table for the MAD results for each approach, we find that MAD for the first approach is 10.42. For the second approach, MAD is 11.65. For the third approach, MAD is 11.19. Again, these represent the average absolute deviation of each month's forecast from actual sales of that month, regardless of the direction of the difference between forecasts and sales. To reiterate, this provides an assessment of monthly accuracy rather than overall accuracy after 2 years' data have been collected. Based on this table, it appears that the first weighted moving average approach is the best, with the lowest MAD of 10.42 units. This means that the forecasted sales for each month differed from actual sales for that month by an average of 10.42 units. Sometimes the forecasted sales for a given month was higher than the actual sales, sometimes it was lower. This table presents the MAD analysis for the same sales data as the previous tables, this time using 3 approaches for the exponential smoothing forecasting model. The first approach, in columns 5 and 6, presents forecasts using a smoothing constant, or alpha, of 0.1. The second approach, in columns 7 and 8, presents forecasts using an alpha of 0.2. The third approach, in columns 9 and 10, present forecasts using an alpha of 0.25. Remember, the higher the smoothing constant, the greater is the assumed impact of current month's actual sales on the actual sales of the forecasted month. The mean absolute deviation, or MAD, for alpha of 0.1, 0.2, and 0.25 are 10.62, 10.06, and 9.99 respectively. The resulting best exponential smoothing approach for forecasting is assigning a smoothing constant, or alpha, of 0.25. In this approach, the average absolute deviation of the forecasted monthly sales from actual sales was 9.99 units, less than the difference for the other 2 approaches. Note that in this table, each approach represented a gradual increase in the smoothing constant, and that the best approach in this example was the one with the highest smoothing constant, that is, the approach that assumed the strongest impact of current sales on future sales. It might be instructive to carry out the table further, with additional approaches using a continuously higher smoothing constant. There may likely come a point where an additional increase in the smoothing constant would actually result in a higher MAD. That is, MAD may decrease with an increase in the smoothing constant up to, for example, 0.4, after which MAD begins to increase. You can compare the MADs across these three different tables, the moving average, the weighted moving average, and the exponential smoothing model, to determine which of these models is best. So we know that, in this case, the exponential smoothing model that used a 0.25 alpha is actually superior than any of the not only exponential smoothing models, other exponential smoothing models presented, but also the moving average and weighted moving average models. The previous three models just discussed are used for short-term forecasts in that they are focused on the impacts of recent period sales on forecasts for sales of upcoming periods. For intermediate and long-term forecasting, linear regression is appropriate. It does not utilize mean absolute deviation, but instead utilizes a statistical method called least squared regression. The process for conducting linear regression modeling is as follows. Monthly sales data is collected, often years in the past. Other factors are considered and applied. These may include external factors such as seasonality and cyclical changes in demand trends impacting sales, and other external factors that finance managers are able to identify and quantify their effects on changes in sales over time. From this information, a linear regression model created that is expressed as y equals alpha plus b1x1 plus e, where y on the left side of the equation is actual sales. Alpha is the assumed sales for a period in a vacuum, that is, what the sales would be without taking into consideration any of the external factors that might influence sales. The x value, or values in the formula, represent the existence of external factors that management has determined will impact sales. Additional external factors would be noted in the formula by x2, x3, and so on. The b value in the formula represents how much x influences sales. The e value in the formula is error. This recognizes some impacts on sales are not measurable with the external factors considered, and that some changes in sales represent randomness or noise. Be sure to read the section in the textbook on linear regression and forecasting. There you will get a much more detailed and specific description of this tool than is possible on a lecture such as this. You will also cover this tool, linear regression, in detail in the Masters in Tourism Management course entitled Tourism Quantitative Analysis 1. The key now is to get a sense of how this tool applies to forecasting sales of your tourism product or service. This figure shows how information generated from a linear regression model can be graphed and applied to sales forecasting. Along the left vertical axis are sales in dollars, and horizontally along the bottom of the figure is time, in months. The sales data used to create this figure is the same data used in examining the other time series forecasting models. The first 24 black boxes within the figure represent a scatter diagram of the actual sales per month. The last 9 black boxes represent forecasted sales based on the assumed impacts of external variables on sales into the future, which may differ from month to month due to factors such as seasonality, cyclicality, or any other external factors relevant to the tourism business. These forecasts are obtained by applying the regression equation y equals alpha plus b1x1 plus e to the data. The straight line is the regression line, which shows the forecasted trend in sales without taking into account the values of the various external factors at a given time. It serves to smooth out the variable impacts of external factors on sales and allows the finance manager to identify the general trend of sales over time. If the relationships used in the regression equation holds, the actual sales should follow that line with the same type of external factor variation shown in previous months. This ends Lecture LM5c on forecasting and time series modeling. Please continue to Lecture LM5d Pro Forma Financial Statements.